Hello, everyone. Good morning, afternoon, or evening. Dear authors and invited guests, welcome to Technical Session 7B. My name is Alesha Mullah, and this session will be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Conference on Information and Communication Technology for Sustainable Development, ICT4SD 2026 in Goa, India. The 11th edition of the conference is being organized in a hybrid mode. The physical event was held yesterday in Goa, and the virtual event is being held from 9th to 11th July via Zoom. I hope you will enjoy the knowledgeable and interactive sessions throughout the day. In this session, we will have 10 presentations. Each presenter will be given 10 minutes for their presentations and 2 minutes for question and answer. On the 9-minute mark, I will raise a gentle reminder. There is another request to all the participants. Please stay connected with us till the closing remarks. If you have any query or update, then you can write it to me in the chat box. Just before we start the session, I would like to introduce you all to the chair for today's session. Dr. Kalyan Bamane is a professor in the Department of Computer Engineering at Indira College of Engineering and Management, Pune, Maharashtra, India, with 22 years of distinguished higher education experience and maintaining a portfolio of 29 plus international publications. His areas of specialization include computer networks, cybersecurity, distributed systems, and software engineering. Welcome, sir. I request you to please say a few words.
Am I audible, Alesha?
Yes, sir.
Yeah, good morning. Thank you very much for giving me this opportunity. I hope am I audible properly?
Yes, sir.
Yeah. This particular conference having full insights about the recent trends of AI. I'm very much thankful to giving me the opportunity to serve as a session chair for this particular session. I hope all the budding researchers will present their topic in a such a way that will be useful for the real-time application. And thank you very much. Over to you, Alice.
Thank you, sir. Now, let's begin with the presentations. Our first presenter for today is Kiran Amar, who will be presenting comparative analysis of RRC functionalities in NB-IoT and 5G NR. You may now begin your presentation.
Yeah, I'm audible, madam?
Yes, you are.
Okay, thank you. Is my screen visible?
Yes, it is.
Yeah. Good morning, all of you. Yeah, myself is Kiran Yamar. I'm working as a scholar in KLE Technological University, Hubli. So my topic of research is the paper title is comparative analysis of RRC functionalities in NB-IoT and 5G NR. So my presentation contents is like this, starting with introduction, research motivation, objectives, NB-IoT and 5G NR RRC mechanisms, methodology adopted, results, summary, conclusion, future work, and the references. So as you know that the growth of IoT applications, that is the rapid expansion of IoT applications, has significantly increased the demand for efficient and scalable wireless communication technologies. So modern IoT systems involve a large number of low power devices that transmit small amount of data intermittently, requiring communication solutions that are energy efficient, reliable, and that are capable of supporting massive connectivity. So there is a need for efficient and scalable communication. So in view of this, there are two emerging technologies, the NB-IoT and 5G NR are the key IoT technologies. So in these two technologies, there is one important layer that is RRC layer. That is we call as a radio resource control layer. which plays the very important role in basically managing the connection setup, maintenance, mobility, and resource allocation between the user equipment and the network. So here, the research motivation basically is NB-IoT uses two states, RRC idle and RRC connected states. So which basically cause the frequent setup or release, which increases the overhead in the NB-IoT networks. So in the meanwhile, 5G NR has introduced one more state. It's called as the RRC inactive states. So which wherein we can bring the device from the connected mode to the inactive mode when there is no data to be transmitted. So in view of this, I worked on this RRC inactive state, wherein I can say that this state basically used in reduction of the signaling overhead. So in view of this, I try to compare these two technologies, NB-IoT and 5G NR. So main objectives of this study was compare the NB-IoT and 5G NR RRC mechanisms, evaluate the signaling overhead, analyze the latency, efficiency, and the PRB utilization. So RRC mechanism with respect to NB-IoT and 5G NR, we have NB-IoT, we have two states, RRC idle and RRC connected states. So which cause the full setup required from it carries the RAS procedure from the idle mode to the connected mode, wherein the four steps are involved, which causes the high signaling overhead and the latency is more. So on the other hand, we have 5G NR, which are at three states, RRC idle, inactive, and the connected states. So because of the inactive state, there's an intermediate state between the idle and the connected mode. So this inactive state has the fast resume procedure with reduced signaling and energy consumptions. So the methodology which adopted is IoT traffic generated. So I use the Poisson's traffic, that is a common traffic for both the models, that is NB-IoT model and the 5G NR model. So and try to evaluate the performance parameters like signaling, latency, energy, and the PRB utilization. So this work basically presents a simulation-based approach to evaluate the RRC functionalities of NB-IoT and 5G NR under identical traffic condition. That is identical traffic. I consider the Poisson's traffic. So the methodology goes like this: a simulation setup wherein EV count, a simulation time, RRC timers for each of the technologies have been put here. So this traffic generation uses Poisson's traffic arrivals, packet timestamp creation. So parallelly, there are state machines for NB-IoT and 5G NR, which are going to monitor the transitions of the states of each of the EVs. So whether the EV is in connected mode or idle mode or inactive mode. So based upon that, the state machine used to get updated. So this state transition basically use the data transmissions, that is RRC setup, RRC resume, and the data transmission procedure is performed. And the performance matrices which I evaluated is signaling overhead, latency, paging events, connected time. So on this, there are certain graphical analysis being done, so which I'm going to show you here. So what the parameters I consider for the input is number of IoT devices, 200 devices I consider, and traffic model is Poisson's traffic, and the simulation time is around 200 seconds, and the packet size chosen is 200 bytes. So what we observe from this RRC events and packet generation, which we can see here, that is yeah. So suppose example we consider here EV3 packet generation ID number 1. So parallelly then NB IoT for NR. So user equipment 3 perform large setup. So number of messages is 6 and transmission packet is 1. That is latency is 1.25 seconds. Similarly, for NR device, performs RS setup to the connected message 6, transmission packet is 1, and but latency is lesser compared to the NB-IoT device. So it's 1.05 seconds. So this is wherein the timestamp which indicates the different EVs doing the setup procedure from setup to the connection mode. So I try to evaluate the signaling overhead. What this diagram shows here, that is the signaling overhead analysis, basically the signaling activity during the simulation. NB-IoT exhibits the more frequent connections here. So you can see the blue one, more signaling peaks due to the repeated full RRC setup and release for the sporadic data transmission. In contrast, 5G NR has having the inactive state mode here. So wherein when there is no data to be transmitted, it does not come to idle state. Instead of that, it shifts from connected to the inactive mode. When any data is to be transmitted, it again goes from inactive to the connected mode. So the fast resume is possible here. So in contrast, 5G NR utilizes this RS inactive state for fast connection resumptions, significantly reducing the signaling overhead and improving the efficiency for the large scale deployment. So on the other hand, this side, the graph, that is latency distribution, CDF analysis. So this graph, it shows that the CDF of uplink latency for both the technologies. The result indicates that the 5G NR achieves considerably lower transmission compared to NB-IoT. One more is energy efficiency analysis graph. So this graph basically shows the connected time per UV. So NB-IoT devices remain connected longer. The blue one, which you see here, the blue one shows that the NB-IoT connected longer time, leading to higher energy consumption. In contrast, 5G NR reduces active connection time using RRC in active state, thereby improving energy efficiency while maintaining quick access. On the other hand, this side, the PRB utilization, comparing this PRB utilization, that is energy resource utilization is critical for IoT networks. So NB-IoT exhibits higher PRB usage due to the frequent RRC connection procedures, resulting in longer resource allocation. In contrast, 5G NR leverages RRC in active state to enable the fast resumptions and reduce allocation time. So the PRB utilization results, what it shows that it is for NB-IoT it is 0.62, while for 5G NR is 0.44, indicating the improved efficiency in 5G NR. So summary of this simulation, total packet generated is 779. So NB-IoT transmits 717. See, I am considering both as the Poisson's traffic. So success ratio is same, but signaling messages, what we can see is 4,350, whereas for 5G NR, signaling message is reduced 3185. And paging events is 136 for NB-IoT and 105 for 5G NR. Whereas uplink latency for NB-IoT is 0.88 seconds, whereas for uplink NR is 0.367 seconds. And energy consumptions, also NB-IoT consumes more energy and NR consumes the less energy, so lower is better. So when I compare both the technologies, I say that 5G NR performs better because of the inactive state, which is present in the 3GPP release 15. So overall, the RRC inactive state improves efficiency, suitable for massive IoT. So in future, we can adopt the cross-layer optimization. That is, we can consider RRC state. Using that RRC state, we can go for taking the context of RRC, then MAC does the scheduling, then the physical layer. So this is the future scope what we have. In. So there are some of the references. Okay, thank you.
So may I ask you one thing? What type of newspaper survey you did to just newspaper?
Yes, sir.
Can you tell me about your newspaper from where you got it?
Pardon, sir.
Dr. Bamani, your audio is actually very unclear. Could you please try speaking up a little bit?
Hello, madam. Yes, ma'am.
Yes, I think it appears that Dr. Bamani is having some technical issues. In that case, we'll just move on to the next presentation. Okay, Dr. Bamani, you're back. Would you want to ask any questions?
Am I audible now?
Yes, sir.
Yeah, could you please tell me about the best paper and how you got the motivation for the research?
Pardon, sir.
Dr. Bamani, could you please repeat the question?
What is the best paper he referred and what would be the motivation behind it?
What, sir?
So I think that trying to ask what was the best paper you referred to and what is the motivation behind your research.
Yeah, yes.
Pardon, madam. I'm not getting you properly.
I believe there's being some miscommunication or technical issues, so I think we'll move on to the next paper for now. Thank you so much for your presentation. Just a moment. All right. Our next presenter for today is Arshi Narsapurkar, who will be presenting Cost-Optimized Cloud Service Recommendation System. You may now begin your presentation. Is Arshin or any of his co-authors present in the meeting today?
Yes. Am I audible?
Yes, you are.
I will require 2 minutes. I am having a technical issue right now.
All right, no issues. In that case, we'll move on to the next presentation and we'll circle back to you later on.
Okay.
All right. So in the meantime, our next presenter is going to be Nasser Anwar Saad, who will be presenting early stratification of type 1 diabetes risk in children aged 0 to 12 using interpretable artificial intelligence models focused on autoantibodies, C-peptide, and HLA-DR3-DR4 DQ8 markers. You may now begin your presentation.
Yeah, good morning, everyone. My name is Nasura Nursad. Today I'll present our research titled Early Stratification of Type 1 Diabetes.
I'm so sorry to interrupt. I think you're muted.
So sorry. Morning, everyone. Okay. So today I'll present our work research that the early stratification of type 1 diabetes risk in children aged 0 to 12 using interpretable artificial intelligence models. So this research basically focuses on identifying children who are at risk of developing type 1 diabetes before symptoms appear. Just like instead of waiting until the disease is diagnosed, we use interpretable artificial intelligence together with biological and genetic markers to estimate each child's level of risk. So moving to the next slide, why is early detection so important? That's like a general question. So type 1 diabetes develops gradually over time, right? So before a child starts showing symptoms, the immune system has already begun attacking the insulin producing beta cells in the pancreas. Unfortunately, many children are only diagnosed after developing serious complications such as diabetic ketoacidosis, which can be life-threatening. So in child, this challenge is even greater because medical resources are limited and there are currently no long-term studies following children at risk. That is why we wanted to create a simple and interpretable AI model. Instead of being a black box that gives predictions without explanation, our model clearly shows why a child is considered low, moderate, or high risk. So this makes it easier for doctors to trust and use. So this slide basically explains how our system works step by step. First, we collect data from siblings or patients with type 1 diabetes as well as healthy controls. Next, we process the data, pre-process data. This means cleaning missing values, normalizing measurements, and preparing everything for analysis. Then comes the feature engineering. So here we select the most important biological and genetic variables such as autoantibodies, C-peptide, and HLA genes. So these variables are then entered into a logistic regression model. We chose logistic regression because it is accurate, right? So it is simple to understand and interpretable. Finally, we validate the model while keeping family relationships together since siblings often share similar genetic characteristics. So the model produces three outputs. As you can see them here, the probability of developing type 1 diabetes, and you have a risk category and a family level summary. So now let's look at the variables used in our prediction model. The first group is HLA genetics. Certain genes, especially HLA, DR3, DR4, and DQ8, are known to increase the genetic susceptibility of type 1 diabetes. So for that, the second group consists of autoantibodies. So these are proteins produced by the immune system that mistakenly attack the pancreas. So we included the anti-GAD65, EAA, IA2A, and ZNT8B, T8A because they often appear years before the disease becomes visible. So the next is the C-peptide, the biomarkers. This biomarker measures how much insulin the pancreas is still producing. So we have the lower C-peptide usually means the beta cells are being destroyed. Finally, we included the simple clinical information such as age and sex. Notice that we intentionally exclude blood glucose, HbA1c, and BMI because those markers usually become abnormal, right, after disease has already progressed. So we have this table. This table basically summarizes our model's performance. So We tested the model using simulated data sets of different sizes. With only 40 patients, the performance appears extremely high, you can see here. Uh, so, however, this is likely due to small sample size, which can make models look better than they really are. At 100 patients, the result become more realistic. Finally, with 500 patients, the performance becomes stable. As you can see, the AUC is around 0.67. Although this is moderate, right? So the AUPRC remains high at about 0.87. This means the model is still effective at identifying children who are actually at risk. So the interpretability, this slide basically shows which variables have the greatest influence on the prediction. So we use something called the odds ratios. An odds ratio is greater than one basically means that the variable increases the risk. When the odds ratio is less than one means it decreases the predicted risk. So the strongest predictor in our model is anti-GAD with an odds ratio of about 1.6. This means children with anti-GAD antibodies have a significantly higher probability of developing type 1 diabetes. So the next important predictor is HLA-DR3, which also increases genetic risk. On the other hand, C-peptide has an odds ratio below 1. So the advantage of logistic regression is that every prediction can be explained using these odds ratios. So here, instead of just giving only a number, our model classifies each child into one of three risk levels. So if the predicted probability is below 0.33, the child is classified as low risk. So only routine annual monitoring is recommended. If the probability is between 0.33 and 0.66, the child is considered moderate risk. So these children should undergo additional biological testing approximately every 6 months. Finally, if the probability is above 0.66, the child is classified as high risk. These children require intensive follow-up, repeat antibody testing, and HbA1c monitoring. So moving to the next slide, this slide shows how the system could be used in everyday clinical practice. So first, the healthcare provider identifies the family and record all available information. Second, laboratory results such as autoantibodies, C-peptide, HLA type, age, and sex are entered. So third, the AI model automatically calculates the probability and assigns a risk category. Fourth, families with several high-risk children can be prioritized. So finally, the last part, doctors schedule follow-up visits according to each child's level of risk. So this creates a simple workflow that helps healthcare professionals focus their attention where it is most needed. So of course, you have our limitations and perspectives. There is no research that is perfect, right? So it is important to discuss our limitations. So the first limitation is that our study uses simulated data rather than real clinical data. Therefore, this result should be considered proof of concept. Second, the outcome is based on biological markers instead of long-term clinical follow-up. So third, the model has not yet been validated outside this setting. So finally, the risk thresholds are practical estimates and may need optimization. So looking ahead of our next objective is to build a real prospective cohort of children in Chad. We also plan to validate the model in other hospitals, compare different prediction time horizons, and optimize the thresholds according to local healthcare resources. So to complete our study demonstrates that an interpretable AI model can estimate the early risk of type 1 diabetes in children using immunological, and genetic markers. So the model is transparent, reproducible, and suitable for resource-limited settings. So among all predictors, anti-GAD and HLA, DR3 contributed the most to the predictions, which agrees with previous scientific studies. However, this remains a proof of concept. A prospective clinical study with real patients will be essential before the model can be used routinely. Thank you very much for your attention. I'll be happy to answer your questions.
Hello. On behalf of Dr. Vimani, I'll be asking the questions which he's put down in the chat. So the first question he wanted to ask was, how did you collect the samples? Was the data set a real one or was it synthetic?
Okay, that's a really good question. So those samples, it was simulated, right? So we had 40 patients, 40 samples data set that we collected, and then it was sent to France for laboratory purposes. And for now, we like being collected from 40 children and sent for laboratory analysis. However, because these results are still pending, right? So that's why the team used the complete information available from 4 patients, these 4 patients. So to generate simulated data set of 40, 150, 500 patients, as we saw before. So these simulations were used to evaluate the behavior and stability of the model, not to replace the real clinical validation, but still, again, waiting for the real clinical validation. Thank you.
All right. Had you tested with any real-time application?
Pardon? Come again, please.
Had you tested with any real-time application?
Not yet. We haven't tested yet.
All right.
We're still again waiting for it. Yeah.
All right. How did you achieve the accuracy and what is the total complexity required?
How did we achieve the accuracy? Okay, here from it was achieved by combining well-established like immunological and genetic predictors of type 1 diabetes, right? So using the interpretable logistic regression model, we selected variables that are strongly supported in the medical literature, including, as we saw, HLA genes, O2 antibodies, and C peptide. So from those, the model was then evaluated using family aware, and as you saw, I think in the ninth slide, and on simulated data set of increasing size. So as the sample size increased, the model's performance become more stable. So suggesting that the selected filters were informative for predicting risk.
All right. Thank you so much. Let's move on to the next presentation now. And next up, we have Aditya Singh, who will be presenting Efficient Retrieval Augmented Generation for Edge Environments. You may now begin your presentation. Is Aditya or any of his co-authors present in the meeting?
Yeah. I am present. Give me a second. I will share my screen.
All right.
I hope you can see my screen. Give me a second. Okay, how do you? Yeah. Is my screen visible?
Yes, it is.
All right. So today I will be presenting efficient retrieval augmented generation for edge environments. So the content of this presentation will include an introduction, which will define the motivations behind this paper, the problem definition, the problems we are trying to solve, the methodology, the results we have observed, and the conclusions we have drawn from those results. So introduction. Let's first talk about what retrieval augmented generation is. Retrieval augmented generation combines external knowledge with LLMs. So LLMs, as you are all aware, are generational models which generate text and allow for processing of large amounts of data in a way a human would. It helps answer questions beyond the model's training data. So initially, an LLM may only be capable of answering questions on the data that it has been trained on. But if we augment it with retrieval, it becomes possible for the LLM to answer questions that are outside of its training scope. So data that might be proprietary, data that cannot be used for training, data that might be sensitive, might have healthcare information or personally identifiable information. That data cannot be used for training because the LLM could, in the future, use that data to generate a response. Hence, this data must be passed through some other means to the LLM. And an approach for that is retrieval augmented generation. It is widely used in chatbots, search systems, healthcare, finance, and enterprise AI. Yeah, so this is the introduction. The main problems, the main motivations behind this paper is that using LLMs in edge environments, as in hospitals, in ships, in environments where large-scale computers, which are required for LLMs, are not available, is quite challenging. Say, if you want to use an LLM in a hospital, you would have to use the API, right? And the API would be run on some cloud provider. The problem is that India currently does not have any large scale uh, GPU infrastructure to allow running LLMs, right? And the DPDP Act prevents sharing data, medical data, and personally identifiable information, financial data outside of India. So that data must be processed within India itself. Hence, organizations that want to use LLM for processing this data from generating insights for the data have no viable choice. They could use edge environment LLMs, but they uh, perform pretty badly because the token count is very small, parameter count is very small. So we tried to implement RAG that is optimized for low parameter models, models that have a parameter count of less than, say, 16 billion or 32 billion. So yeah, so the key limitations that we identified of a traditional RAG system is it relies on fixed size chunking. So chunks are created in fixed size, and each chunk contains a certain number of tokens. And at the time of retrieval, a certain number of chunks are collected and provided to the LLM as context, and the LLM uses them to generate response, right? The problem with fixed size chunking is it does not take into account the meaning semantics of the document. So oftentimes it will include irrelevant information that is not necessary for the particular query. If it or sometimes it would contain incomplete information. So yeah, important context is often missing, and the token count becomes quite large because we are not considering the similarity to the query. So the methodology, we wanted to boost the low parameter model reliability, preserve semantic coherence during chunking, and reduce input token count and hallucination rates to enable practical deployments on edge devices. So yeah, this is the formula that we utilize for efficient chunking. So whenever we're creating a chunk, we do this sentence by sentence. Initially, the current count of tokens is taken, which is the current size of the chunk, union the next sentence, and the token count is multiplied with the factor alpha and a value beta, and similarity of the current sentence with the existing chunk is taken into account. So if the next sentence is very similar to the current chunk, then that sentence would be included. It has a higher likelihood of being included. Otherwise, a chunk boundary might be created. So that is the formula we are utilizing for efficient chunking. It ensures that chunks never get too large and semantic meaning of each sentence is taken into account during this process. Apart from that, we are utilizing a graph-based retrieval mechanism. So we calculate the similarity of the query with each node, and we traverse the graph. The traversal is subject to a limit. So the token count of all of the selected nodes, selected chunks, must be lower than a limit L. So yeah, you can look at this formula. This is the graph visualization that we developed, and here the thicker lines represent a more semantically similar chunk. So these chunks are related, and on the basis of this graph, the traversal would take place. All right, so this is the architecture. Initially, we have documents, text is extracted using PDF modification parsing libraries. Apart from that, we run it through the token efficient chunking algorithm. We create embeddings. These embeddings are stored in the vector database, and they are also given to the graph engine, which creates this whole graphing system. Apart from that, whenever a user gives a query, an embedding is generated for the query. The most similar uh, chunk is located, and then graph traversal takes place from there. The retrieved chunks are passed to the LLM, and the LLM generates the response. So results methodology. After building the system, we wanted to test it out against a traditional RAG and a traditional LLM. So for the standard RAG, we utilized the Lewis et al. Paper, the original paper introducing retrieval augmented generation, and we used the methodology they had defined to implement the RAG. It was utilizing top 3 retrieval, and it was tested on low parameter models. So we used 4 open source models. We had Gemma 2B, Gemma 4B, Llama 3B, and Llama 8B. We gave them identical queries and knowledge sources. So for this, a book regarding medicine was utilized, and queries for different diseases, what should be used to treat different symptoms was utilized. We measured the token usage of this, hallucination rates and response quality. So the response quality check was quite subjective. We had a team of 5 evaluators score the responses. They had no idea which model was responding to the query or which RAG architecture was being utilized. We also manually verified hallucination rate. So whenever an LLM came up with completely made up information, we counted that as one, and we also checked for partial hallucinations where the LLM is creating some information that is not really backed up by the knowledge source that had been provided. Observations. So we observed that the baseline RAG used about 1380 tokens per query. The modified RAG used a maximum of 500 tokens. So that was a limit that was set. According to this formula, you can see there is a limit parameter. So the limit parameter was set to 500. According to that, the tokens were fetched. Hallucination rates decreased across all models. So irrelevant context was reduced, and hence hallucination rates were lower. Smaller models showed the largest improvement. So smaller models showed significant improvement in reduced hallucination and also showed improvements in quality. Response quality improved for 3 of the 4 models. Again, response quality is subjective. I would not say it is completely objective. It does not utilize a benchmark because running benchmark with these models is quite challenging and requires a significant amount of compute. Llama 8B remained close to baseline with fewer tokens. Right. So you can see this is
Excuse
the.
me. I'm so sorry to interrupt. You have 1 minute left.
All right. Let me go through the results real quick. So these are the hallucination rates we observed. We observed that Gemma 2B had 7 hallucinations in the baseline, and in the modified architecture, it had 6. Similarly, for Gemma 4B, we had 7, and yeah, so on and so forth. You can see that in the quality parameter, we can see that the quality difference is not that large, but it is still significant considering that the amount of tokens utilized by the modified RAG architecture was less than half of the tokens utilized by the baseline RAG architecture. So yeah, this has all been discussed here. Yeah, any questions?
Hi, Aditya. I'll read back the questions that Sir has written down in chat. First
Yeah.
of all, your topic is good, and he wanted to ask why only RAG with LLM?
I don't understand the question, like RAG with LLM. So retrieval augmented generation is typically used with RAGs, LLMs only. I have not heard about other approaches, other use cases.
All right. His second question was, is there any integration? And if so, then what are the comparative parameters for results?
Uh, Integration. Could you clarify the question, sir? Integration.
Integration of models.
So yeah, we tested it out in an integrated manner. So we were running these LLMs using an API. Again, we did not have sufficient compute, but all of these LLMs can safely be run on a local machine. So say you wanted to run these LLMs, you could run them on a GPU with, I think 4 GB of VRAM should be sufficient. So yeah, these are definitely very efficient small scale LLMs. Yeah.
All right. Thank you so much.
Yeah.
We'll move on to the next presentation now. We'll now be circling back to Arshin Narsapurkar, who will be presenting cost-optimized cloud service recommendation system. You may now begin.
Hello, am I audible?
Yes, you are.
So, okay, I'll be sharing my screen now.
Hello, ma'am. Good morning.
Hi, Ashi.
I think there's my number after Aditya.
There is, but due to a technical glitch, we had skipped over a presenter before. We'll just circle back to that, and you're right after.
Is my screen visible?
Yes, Arshin.
So, okay, good morning, everyone. I am Arshin Narsapurkar from the Department of Information Technology at SIS Graduate School of Technology, Navi Mumbai. And so let's begin. So my topic is cost optimized cloud service recommendation system. So as we all know, over the past decade, organizations and even individual developers have rapidly adopted cloud computing because it offers scalability and flexibility, and also the cost aspect of it, as many developers do not have the compute power. However, this flexibility also creates a challenge. Organizations and individuals often provision resources quickly, but rarely revisit whether those resources are still required. So this is the cloud cost problem that is heavily affecting the industries right now. So the industry reports estimate that 25 to 32% of all cloud spend is wasted. The root cause is that the engineering actions and the financial visibility is decoupled. So basically what happens that is when in a company, the financial team assigns a budget, the budget is then taken by the developers, but it's not really aligned with the cloud providers. The cloud providers have a dynamic pricing that the developers don't really understand nowadays because it's quite complex, and that is the reason that it's a huge problem as of today. And the research limitations in this topic are that there is a tool called the AWS Trusted Advisor and Compute Optimizer, but it is heavily siloed and it lacks a multi-service context. So basically, it has only specific context and specific service recommendations. And the rule-based systems are quite brittle and they need to be hard-coded every time you have to train. Basically, you have to look for optimizations in your own architecture, which is quite limited. And the current research focuses strictly on anomaly detection with no emphasis on active remediation. The missing link here is that there is no existing system that directly translates the engineering demands of the cloud architecture into deployable infrastructure as code. So this is our contribution. It's also known as infra trim, which is trimming the infrastructure costs. So what we have done is that we have uh, went over an aspect of multi-service optimization, which evaluates multiple services. And we have used random forest classification because our data is structured tabular data and it works best. And it's also quite simple as of now. And we also have direct IAC generation, which is infrastructure as code. So there's a language called Terraform, which translates the cloud architecture into the code, basically it takes a code in the HashiCorp language and it translates your architecture into the infrastructure in AWS. So this is the system architecture. So the client, whether it be an organization or an individual developer, he or she goes to the client browser and then uploads the AWS CSV, which includes different types of features for these services like compute optimization, network input output, memory utilization. And then it goes to the React frontend, which uses Nginx, and then goes to the APIs to the Flask server, which uses Green Unicorn and Docker. And it has two workers, so it can serve multiple requests at once. And then it goes to the random forest engine, and then the classification labels are encoded, and then it provides the results as JSON plus Terraform outputs. So JSON is also used in AWS to basically script the architecture. The machine learning model that we have algorithm is random forest classifier, and it was much better than an individual decision tree, as there are 100 estimators and we can aggregate the decisions that I've made. And these were the input features that we have put, which is like service, instance type, region, cost, etc. The target classes which AWS has is like, if there's a service like EC2, then either the user should downside or upsize, or if there's S3, which is the storage service from AWS, they can move to Glacier or they can use intelligent tiering. And we have used random forest because it has high interpretability and it is robust to non-linear relationships, and it also handles overfitting really well. So this was the implementation stack, as I already explained. We basically Dockerized it on multi-stage builds using Green Unicorn. Uh, these are the results. The model accuracy was 94.2%, and we tested it on 10 beta users. So this is actually a live website that anyone can use, and they can upload their CSV. So we had 10 beta users validate this, and the model accuracy was for each of the unique data sets that the 10 users presented. The model accuracy was 94.2%, and the average cost savings that the infrastructure yielded across synthetic and also real benchmarks was 29.5%, so it is around 30%. And the feature priority that we gave was the CPU utilization and other metrics which are quite important in determining the costs. So here's a script of basically how it provides a script. AMI is basically the Amazon machine image, which is a configuration of your architecture. It shows everything, which is the instance type, the CPU, the memory you are using, the storage, the network, and the estimated costs. And these are the recommendations, like the organization on the user can then act on these recommendations. Like if you have to downsize it, if you have to put the storage into intelligent tiering, and you have to basically use a reserved instance type of EC2 type, which is much more cost optimized than the other types such as spot or on demand. And one of the biggest cost waste reasons for waste of spending is unused EBS volumes. So EBS volumes are basically they are storage volumes, block volumes, which are attached to the EC2 instances that the developers use. And many times the EBS volumes are stay unused or even unattached because they are quite separate. Like you can create multiple EBS volumes for one EC2 instance. So it is quite confusing and also quite dynamic. So there are some limitations although. So current validation relies heavily on synthetic and semi-synthetic as the beta users and lacks exposure to massive scale enterprise data. Enterprise data is basically big data, right? So what we are lacking is that a huge scale is needed to even further validate our research even more. API integration, we only have manual CSV and not the live AWS, as cloud environments are really sensitive. So we don't really have that integration right now. And the Terraform that is generated is quite simple and it has to be manually reviewed as of right now. So the future work is we are looking to upgrade the algorithm, transitioning to sequence models and predictive scaling. Predictive scaling is basically when you scale the demands of the scale the infrastructure according to the demands that you're predicting. Ecosystem expansion. There are multiple cloud providers, not only AWS, but AWS is the biggest one. So we decided to work on AWS for now. But in the future, we also look to develop our application and our research towards different providers and different dynamic systems such as Azure and GCP and command line integration. So users can then develop using CLIs, and then they can understand their own cost even before deploying it in the CLI itself. And a huge factor is green ops. Green ops is basically these compute these compute that we save, the compute waste that we save. It also saves carbon savings. So carbon is emitted when you use compute, right? When you use electricity, when you use computers. So what we are trying to do is we are trying to save the compute and also save carbon. So this is the conclusion. And as we all know, visibility is not enough. Identifying waste and also what required is actionable insights. And in the future, we obviously aim for green ops, which is a huge part of our research scope. And everyone nowadays tends to look at carbon energy and all those things that quite important due to climate change and global politics and all. So we look to expand this towards that, and these are some of the references. And if there's any questions, and these are my email, and there's also the URL that anyone can visit and also use in if you have to understand the project even more. So thank you. And if there's any questions, I'm open to it.
Thank you, Arshin. Uh, how is the accuracy calculated, and what is the efficiency of the algorithms that you've used?
The accuracy is calculated using the random forest model. What we have done is that we have used 10 beta users, like if we have 10 developers, and we told them that you have to basically put your AWS data in our website, which is not that safe, as I told, but it was calculated using the random forest model. And the efficiency was quite good, as random forest is quite lenient in terms of overfitting. If we use XGBoost or neural networks are quite good for let's say images NLP, which is not our use case right now, but that was the best scenario that we had as of now.
All right, thank you so much. We'll now move on
Thank
to the
you.
next presentation. Our next presenter for today is Ashi Singhal, who will be presenting Explainable AI in Financial Decision Systems, Addressing Cognitive Bias and Enhancing Trust, a secondary data study. You may now begin.
Hello, good morning everyone. My name is Ashish Singhal and I am from Graphical Deemed to be University. Today I am presenting my research titled Explainable AI in Financial Decision Systems, Addressing Cognitive Bias and Enhancing Trust, a secondary data study. In this study, I explore how explainable AI can help people make better financial decisions by reducing the cognitive bias and increasing trust in AI systems. I also propose a new conceptual framework called the Explainable AI Bias Trust or XBT model. So let's discuss what is the background behind this. So today AI is becoming an essential part of the financial industry because it is widely used in applications such as robo-advisors, credit scoring, fraud detection, and algorithm trading. Although these AI systems are highly accurate, but many of them work like the black boxes because they provide the decisions, but they do not clearly explain how the decision was made. So the financial decisions are not always rational. Investors are also influenced by cognitive biases such as overconfidence, herd behavior, loss aversion, and anchoring. These biases can lead to poor investment decisions. So, because of this, regulators are increasingly emphasizing the need for explainable AI. Explainable AI not only makes AI decision transparent, but also has a potential to help users recognize their own biases. So this helped us to bring my research problem addressed in my study. So what is the gap between AI accuracy and the human trust? Although AI has significantly improved financial decision making, but an important challenge still remains because most AI systems are designed to make accurate predictions. They help users understand their own decision making behavior, but there is a challenge also that there's a trade off between accuracy and interpretability because generally, the more accurate a model, the less transparent it is. So during my literature review, one interesting observation I stood out that users often trust AI recommendations because they trust the explanation, not because the prediction is accurate. So, however, no existing framework connects explainable AI, cognitive biases, and user trust within the financial decision making. So, this research gap became the motivation for my study. So, the three objectives which helped me to guide this study. First, to identify the major cognitive biases that influence the financial decisions. Second, to understand how explainable AI techniques such as sharp, line, and counterfactual explanations can help address these biases. And finally, it is the most important part to develop the explainable AI bias trust model, which integrates explainability, cognitive bias, and trust into a single conceptual framework. To achieve these objectives, I carried out a systematic review of the existing literature. So in the literature review, I reviewed 48 published research papers related to explainable AI, cognitive bias, trust, financial decision making. So the largest group focused on cognitive bias detection, followed by explainable AI in finance, trust in human AI interaction, and AI applications in finance and regulatory frameworks. So most importantly, we found no existing research proposal integrated framework connecting these explainable AI, mitigation, cognitive bias, and trust. So this gap became the foundation of my proposed XBT model. So my research is based on a qualitative secondary data approach using a SLR, systematic literature review. I follow the Prisma reporting framework to ensure transparency and consistency for the review process. We searched 5 major databases: Scopus, Web of Science, IEEE, Google Scholar. So after applying my inclusion and exclusion criteria, I selected 40 relevant studies with 20 studies analyzed in great detail. Now let me introduction the main contribution of my research. This slide presents the main contribution of my study, the explainable AI bias trust model. The model consists of 5 stages. In the first stage, AI generates a financial recommendation such as a loan decision or the investment suggestion. In the second stage, explainable AI provides a clear explanation using techniques like sharp, line, or counterfactual explanations. In the third stage, explainable this explanation helps users recognize possible cognitive biases in their own thinking. As a result, in the fourth stage, users make more informed and less biased financial decisions. Finally, in the fifth stage, the outcome creates a feedback loop that gradually strengthens user trust and supports better financial decisions. So the model is based on three propositions. Explainable AI improves decision quality by reducing cognitive bias. Second, explainable AI increase competence, trust, encouraging users to adopt AI recommendations. Third, repeated positive experiences contributes to strengthen trust by reducing cognitive framework bias over time. So my three findings from literature review: first, cognitive bias are well documented and can increasingly be identified through AI-based approaches. Second, explainable AI techniques are technically mature, but they are rarely used specifically to reduce behavioral bias. And third and most importantly, trust plays a key role in whether users AI accept AI recommendations. So lastly, discussion. These findings are important implication for researchers, industry professionals, and policymakers, for fintech companies, and for regulators. So to conclude, my study proposes this model, the first integrated conceptual framework connecting these in financial decision making. The model provides a theoretical foundation for developing more transparent, trustworthy, and user-centered AI systems in finance. But my study is one limitation that it is based on secondary data, and the proposed framework has not been empirically validated. Future research should validate the model through experiments, develop standardized trust measurement scales, and validate the framework across different financial and regulatory environments. I hope this work encourages further research in explainable AI, behavior finance, and trustworthy AI. Thank you so much.
Thank you, Rashi. Are there any questions from the chair?
Yes, ma'am.
Actually, just one moment. We'll wait to see if sir has any questions.
Ma'am, is there any questions?
There's no questions yet. So if it's okay with you, we'll move on to the next presentation.
Okay, thank
Thank
you
you,
so much,
Rashi.
ma'am, for your time.
Just one moment.
Ma'am, can I leave or we can stay this meeting?
You can stay till the end of the meeting. That would be requested, please. Thank you. Our next presentation would be by Balaji More, who will be presenting Explainable Dual Architecture Deepfake Video Detection, a comparative study of CNN and JAN discriminators across multi-resolution inputs. You may now begin your presentation. Is Balaji or any of his co-authors present today?
Just 1 minute, ma'am.
All right.
There is a technical issue. Can we
Okay,
present
yeah,
next
no
thing?
issues. We'll take you in a while then. We'll move on to the next presentation in the meantime. All right. So our next presenter for today will be Krishna Turkar, who will be presenting SmartPerp, a blockchain-based framework for secure property transfer, fraud detection, and market forecasting. You may now begin with your presentation.
Yes, ma'am, I'm sharing the screen.
Hi, Krishna. Are you presenting?
One minute, ma'am, I'm sharing the screen. Okay. So, yeah. Am I audible?
Yes, you are.
Okay. So, my topic for my presentation is SmartProp, a blockchain-based framework for secure property transfer, fraud detection, and market forecasting. So, my PPT contents are introduction, research objectives, literature survey, methodology, system architecture, implementation, result, and future work. So first, the introduction of my PPT. So we know that the real estate sector is one of the most valuable sensitive dominance where ownership, trust, and security plays a crucial role. So now in a real world, we use a traditional system which rely on centralized uh, intermediaries, creating single point of failure and efficiency. We use centralized systems. We have very, security issues, lack of transparency, and time-consuming process in the real-life traditional system of market of property transfer. So the research objectives of smart props are to secure the property protocols, real-time fraud detection, decentralized registry, and market forecasting engine. So the literature survey, which we have done in our in our research paper, we find the gap that the existing solution address individual challenges in isolation. No prior framework combines blockchain-based transfer, real-time fraud detection, and ML-drive market forecasting. So the methodology which we used for our model is, first we have implemented a blockchain implementation with a Ethereum blockchain network. Then we have done the system design. After that, we have used our ML module training for fraud detection, and then evaluation from the real life data set. The system architecture, which consists of smart contract engine, which use immutable Ethereum contracts, by which a buyer or seller portal is uh, conducted for we either have to enroll documents for the fraud detection module. Then we use the market forecasting engine for future scope of market price is high, or it will be vary on which uh, basis. Then the implementation, the technology stack for the smart pro framework was implemented as a decentralized web application using blockchain technology, smart contracts, and a modern web development stack to ensure secure property registration and ownership management. Was deployed on a local Ethereum testnet with 500 simulated properties transfer for validation. Implementation consists of blockchain, dataset, backend, and security. The security which we have used is SHA 256 hashing for document integrity verification and preventing the data tampering. The result which our model gives is the secure property registration, successfully implemented blockchain property registration using Ethereum smart contracts. Then document integrity using SHA 256 having ensure updated property document remain tampered proof and verified. Then the automated ownership transfer. Smart contracts automate the property transfer process, reduce manual intervention, and improve transparency. Then decentralized framework. The proposed architecture provide a secure foundation for integrating fraud detection and market forecasting for future work. So this is our page which is look like. This is our first page which is uh, here in my PPT. Then there is a seller board where all the personal details and verified KYC details of a user is enrolled. And then there is a market forecasting page where it shows the market growth of the property. So the future work and conclusion of our project is to integrate with government land register APIs to live deployment and deployment on public blockchain networks such as Ethereum, Mainnet, and or Polygon. And we are doing a future work for deploying a mobile application for our uh, model. So yeah, thank you. Any questions?
Uh, Thank you, Krishna. Sir, do you have any questions? All right, there's no questions in the chat currently. Thank you so much. I think we'll move on to the next presentation.
Okay, ma'am.
All right. We'll circle back to the presentation just before this, just a moment. All right. So now we'll have Balaji More, who will be presenting Explainable Dual Architecture Deepfake Video Detection, a comparative study of CNN and GAN discriminators across multi-resolution inputs. You may now begin.
I am audible, ma'am.
Yes, you are.
So, our topic for the this research is explainable dual architecture deepfake video detection, a comparative study of CNN and a GAN discriminator X across multiple resolution inputs. This is my teammates. So the content for this presentation is problem statement, proposed solution, methodology, implementation, results, future work, and conclusion. So the problem statement is that nowadays the deepfake videos are very advanced AI technology enable creation of a highly realistic fake videos that threatens the digital trust and the information integrity. So to answer this, we have to challenge the detection of this AI images. So for modern deepfake contains minimal visual artifacts, making them difficult to identify using the traditional methods. So, what is the limitation? Limited comparative studies for the previous papers. Most existing research papers, CNN and GAN-based detector separately without any direct comparison between them. So, also there is a lack of explanatory in the detection of this deep fakes. So detection system often operates as a black box, reducing the trust in the forensic and the legal applications. So where we in this research we use the explainable AI like Lime and GradCam. The proposed solution is for the architecture detecting the framework, a unified framework that compares the CNN and GAN discriminator architecture for deepfake video detection. Also, we use the explainable AI integration like GradCam and Lime to visualize and interpret the model decisions. What are the resolution we use for the analyzing? There is a first 128 to 128, then second is 256 into 256, and third is a 512 to 512. Also, what are the features, facial features we use for detecting whether the image is fake or real? First is a textual inconsistency. Then there is a eye blink patterns and facial expressions. Also, the boundary artifacts and the lightning inconsistency in the images. The methodology, the dataset we use for this research is a DFDC defect detection challenge. It consists of 324 videos, while the 152 is real and 172 is a fake videos. We use the pre-processing on this data. We do the frame extraction at a 5 frame per seconds. Then there is a HAR cascade phase detection. Then we use the multi-resolution resizing and normalization. Also do the some data augmentation for the better results. Then we can train the do two different models, CNN and again discriminator. In CNN, we use the five convolutional blocks using the batch normalization railway activation, and it is fully connected layer. In GAN discriminator, we use the six convolutional layers having the spectral normalization and instance normalization with the leaky ReLU. This is the model architecture where first we can give the data set of a fake and real image. Then we go for the pre-processing. We can split the video into frame and detect the face. Also, we can crop the face from the images from the videos and save the face for the cropped videos. Then we do the feature extraction from these images. Then we process the data set, then split data set for the training and testing. Then we load data set for our models, GAN, CNN. Then we do the model evaluation, and we can also create the model for the further testing. Here is the implementation. What are the technical stacks we use? Python, TensorFlow, Keras, OpenCV, NumPy, and scikit-learn. Also, there is a training configuration that we use. We use the Adam optimizer, and the learning rate that we use is 0.001, and the batch size is 32. Their hypothesis is 40, and we use the binary cross entropy loss. What are the hardware we use? There is NVIDIA RTX 3080 GPU. What is the data set? It's so we use the training 70%, validation 50%, and testing 15% data. Here are the results for the 256 to 256 size images. There is a CNN performance and a GAN performance. The accuracy of the CNN is 17.1%, precision is 19.8%, recall is 63.8, and the F1 scores 66.7%, and the AUC is 0.78%. Similarly, for the GAN, the accuracy is 69.8%, precision is 64.5%, recall is 79.6%, F1 score is 71.2%, and the accuracy is 0.77. However, the key observation is that the CNN is a higher precision, also the GAN is a higher recall and better defect detections. This is the comparison between the GAN and CNN performance comparison, where we plot the different evaluation metrics like precision, recall, F1 score. This is the confusion matrix that used to calculate the previous factors, accuracy, precision, and recall line. This is the CNN and GAN comparison for the ROC curve. Here is the where we show the Lime explanation and GradCam explanation. Here in the Lime you can see the yellow line that can represent what are the parts of the face that can use for the defect detection, and also the GradCam shows the heat map that it shows the heat map that can what are the parts that actually include in detection of the defect videos. The future work we can do is a video temporal analysis by using the LSTM and 3D CNN for improve the temporal consistency modeling. Also, there is a adversarial robustness. We can improve the resistance against the advanced defect generation technologies. Also, the multimodal defect detection, where we can use the audio, video, and facial signs for detection. And there is a cross data evaluation also, where we use the different data set like fake forensic plus plus CBLD, DF, and DFDC for better generalization of the results. The conclusion, CNN and GAN architecture were compared for the video defect detection. GAN achieved the superior recall 79.6% by capturing the distributal anomalies. CNN achieved higher precision like 79.8% through a spatial artifact detection. 256 into 256 resolution provide the better balance between the performance and the computational cost. Yeah, and the grad and lime improve the interpretability by highlighting the critical facial regions. The framework demonstrate the effective and the explainable defect videos detection for the real world forensic applications. This is the reference. Thank you. Any questions?
Thank you, Amol. There's no questions in chat. We'll move on to the next presentation now. Our next presentation for today is by Pushkar Pandit, who will be presenting spectrophometry using an AI monitoring system for reaction endpoint. You may now begin your presentation.
Yes, ma'am. Can we just have 30 seconds?
All right.
Yes, ma'am. Is my screen visible?
Yes, it is.
Okay. So basically, our topic for today is spectrophotometry using AI monitoring system for reaction endpoint. Uh, for the introduction, let's take an example. Imagine you're a technician in an oncology lab uh, in an pharmaceutical multi-million dollar company. And to get to know which reaction stage the reaction is currently going through, you have to go to a lab, test the sample which you have collected from the container for 45 minutes, and then return and make the necessary changes. Now, this doesn't actually happen in a multi-million dollar company. They, of course, have safety features. They have inline spectrophotometers, and they have a technology called as PAT, the process analytical technology. Now, this technology acts only when such deviations are detected. But what if we decided to detect the deviations beforehand? Uh, our research project does exactly that. It reduces the costs of PATs and additional lab equipment, which is necessary for such pharmaceutical and chemical reaction companies. Uh, it's a industrial IoT project at a glance, but it goes deeper with the AI aspect and the dataset aspect. We have trained a model with limited data, but still managed to land some satisfying results. Now, explaining system architecture, we have used an ESP32 MCU. It is the most common MCU right now. And for the spectral sensor, we have decided to use AS7341, and it is a 11 channel sensor. The reason we have used this, I can tell with an example. Uh, so the ladies, they have developed color palettes. Uh, Normally, they can tell the difference between uh, light pink and pink. While us men, we think that pink is just red. Now, like always, the women here, they are right, and the the following sensor is 7341 is also a similar type. It has 11 channel spectral sensors. It has 11 channels, and and it gives different readings for every different shade. That's its specific. And the following data was tested, and we got the following data was tested in a random forest model. It is the most simple model right now in AI, and uh, it is reported through Telegram bot alerts and remote monitoring. This is the system architecture overall. We are using a 7341 sensor as well as an MQ2 gas sensor. The AI model is basically not dependent on the microcontroller. We can run it in a laptop or a different GPU or even in a Raspberry Pi. This is the data which this is the data set which we collected from an initial test, uh, which I'll be coming back to later on. Now, why did we choose the iodine thiosulfate reaction? First of all, this is a really versatile reaction. As you can see, it goes through many color changes, and that was necessary for us to gather more data on different color shades. Uh, Now, as you can see here, these are the spectral channel characteristics. And in the previous slide, we got the data from test reaction, which we conducted. And the data set which we collected had in total um, 209 training samples. They are less as of now because we had limited chemical resources. We could only we could only make limited reactions using those resources, and we had to train a synthetic. We had to make a synthetic data set from those real readings. Now we have used a random forest classifier here. It was necessary as there are too many variables here, and the pre-processing and uh, it helps with the processing as well. For the data set collection, the most important part while collecting through an actual reaction was the lighting and the environment. The lighting environment is basically necessary here because we used an actual test tube to uh, proceed with the reaction, and we could have got some different readings and different lighting environment because natural light affects the sensor a lot. But in future, we are planning to build a specific box as such to keep the sensor there and get actual and accurate reading. Now, as I said, these are the real world testing and results. We have reported the results through Telegram right now because it was easier for us because we are showing a college professor. But we are also working on MQTT protocols uh, as well, and we are also working on MQ2 sensor assembly as well. We have just uh, tested for a single reaction right now, which is the iodine thiosulfate reaction, but there are multiple such reactions which we need to test upon for the shades and different spectral channel readings. Now, the challenges which we faced here is, of course, the lighting and the real world data set for better generalization. Uh, so yes, this was the real world testing and of course the results. Now, this project is being sponsored by a company. We are currently trying to develop the same algorithm and implement it through Raspberry Pi so that we can just not use ESP32 anymore. So, uh, ending on a note that we had to develop some synthetic data sets for the following project, but we are trying to commit ourselves to run some more reactions like iodine thiosulfate and phenolphthalein reactions to get more data on the following spectrophotometry work. Thank you for your time. Do you guys have any questions?
Thank you, Pushkar. There is no questions in the chat, and so we'll move on to the next presentation.
Thank you.
All right. So our next presenter for today will be Abhilash HP, who will be presenting Twitter Sentiment Analysis in the Era of Deep Learning, a comprehensive review of public opinion mining methods, challenges, and trends. You may now begin your presentation.
Yeah, am I audible, ma'am?
Yes, you are.
Yeah, thank you. Just give me a second. I'm sharing my screen. Yeah, I hope my screen is also visible.
Yes, it is.
Yes, thank you. Thank you. So, good morning, everyone. So, this is Professor Abhilash from Reva University. Actually, I'm pursuing my PhD from Presidency University in School of Information Science. So, my research topic is Twitter sentiment analysis in the era of deep learning. So here, so I am presenting a comprehensive review paper. So based on the public opinion mining methods, challenges, and trends in the current research area. So here, my presentation outlines looks like this: introduction, background, research methodology, challenges, emerging trends, gaps, conclusion and future work, references and questions and discussion. So here, talk about Twitter nowadays. Twitter sentiment analysis basically. So we will find out the public opinion behind the tweets. So as we already know that today the open platform, the Twitter, now it is renamed as X. It is one of the biggest and very huge microblogging platforms where peoples can freely they can tweet their opinions or their thoughts. So now it is the biggest challenge for all the industries nowadays. So to fetch some insights from that particular tweets. So here, Twitter sentiment analysis aims to automatically classify the tweets into positive, neutral, and negative polarities. Nowadays, with advanced tools, we have the polarity states are even more added, right? True, negative, very positive, like that. So we have added so many other polarities as well. So here, Twitter data again. So when the data becomes humongous, what happens because of so many peoples with various backgrounds will communicate there. So there may be chances of informal languages, slang and abbreviations, hashtags, so at mentions, emojis and emoticons usage, sarcasm and irony. So and short text length. Of course, Twitter doesn't allow you to write large paragraph text. It will make you write very small tweets. So and of course, that length is also one of the advantage for our research actually. And so if you take the past decade, so sentiment analysis techniques has evolved from lexicon-based approaches to traditional machine learning, deep learning, CNN, LSTM, by LSTM, transformer-based model, and now it is moved on to hybrid models and explainable AI also introduced into the scenario. So, and here, if you talk about the uh, um, study, see in this study, what we are doing is we are reviewing some major sentiment analysis methods that are already done so far from last 10 years. And so we are, and of course, getting the Twitter data is nowadays live data is very challenging as it is converted to X. Now it requires subscription and it is too costly. So that's why what we are doing, we are finding the data sets already examined by so many peoples, and we are considering the same thing, and we are taking into our research and we are building our own model. and analyze research trends and technological advancements. And so we are identifying what are the existing challenges, and we are finding the future research directions in this study. So, and if you take about the background, so this research survey, so if we take foundational models, there are so many studies talked about foundational models. There, some of the models, BERT, Roberta, and GPT, these are the tools or models they are used. So almost around 80 to 80, 75 to 80% accuracy was achieved at that time. And technological advancements, if you take, so next after foundation modules, hybrid BERT and BioSTEM are introduced. CIG and TMCA framework and Roberta and attention mechanisms are introduced. So there drastical improvements in the results. So almost 98% of accuracy was achieved on Amazon and Twitter datasets. So in domain specific applications, if you come domain specific, so next we got BERT for Amazon Electronics and ExcelNet for medical, or mm, and in stock market HSAP, and Delm for stock predictions and financial trends. If you take, so there we have 80 LSTM model. So here also you can observe the accuracy rates. It is increased from 90 90 almost above 90. And if you come to multilingual models, because nowadays, as we know, the number of users are from various parts of the globe. So there may be chances, there may be different languages, right? So nowadays, for that also, if you take IQAD 31K, this model, so in this model, it is achieved around 95.63% of F1 score for Arabic language. And in ensemble models also for Arabic social media, we achieved it achieved 95.95% of hard voting and 93.79% of uh, slang votings are there. So this was in case of multilingual and specialized category. So this is how our models evolved from a foundational models to a multilingual models. And so nowadays, as already told you, it is we are using explainable AI, and along with explainable AI, so we are using CNN tools and attention mechanisms, BERT and Roberta. So these are the tools we are using to make it hybrid. So so this was the methodology so that we used for our review. So the study was based on systematic literature review. So in this, it identifies and examines the literature from almost 2019 to 2026. This ensures that the study is reproducible and covers all aspects from lexicon based methods to the latest developments in explainable AI and generative models. So here we have two criteria for inclusion and exclusion of the studies. So we included architectural innovation based studies like hybrid models of BERT and BLSTM, cycle GANs, and graph based models. So because nowadays images are more in the tweets, like emojis and emoticons are more instead of textual tweets. So because of that, we need to introduce cycle GAN as a part of our model. And graph based models are also required because to we need to talk our results to the public. So that is the graphs are one of the best suited models to speak that. So we excluded the scope and relevance, so that are not in our scope. So in-depth studies in which the scope of sentiment analysis is not a primary focus. So reporting and quality works in which accuracy and F1 scores are not considered essential metrics, are written in languages are other than the English. And the methodology which we used is Prisma, that is preferred reporting items for systematic reviews and meta-analysis. In the identification stage, we took around 1240 records. So, and after screening, some duplicates are removed and we got 930. And because for our research, we got only 245 eligible documents. And with that, we got only 28 are selected for final study. So this is what the approach that we have used. And here we observed so many challenges. Sarcasm, as we know that sarcasm is one of the most biggest challenge in Twitter sentiment analysis. So, for example, if you take example, great, my phone battery died during the interview, best day ever. So here it looks positive, but actually the sentiment is negative. So, and some multilingual tweets, fake news are there. So fake news will be published in the Twitter. Some people will chat fake, and imbalanced data sets are there in the uh, repositories.
Excuse
Explainability
me.
AI. Sorry.
I'm so sorry to interrupt. You have less than a minute left.
Okay, okay, right. I'll finish. So XI is another challenge now. Explainable and scalability issues are also there. So these are the emerging trends for Twitter sentiment analysis, lexicon, deep learning, transformers, and hybrid XA models. Now the trend is going with hybrid models, as we need to merge so many different technologies together to improve the accuracy of the models. And these are the various gaps we have: multilingual support, context understanding, explainability, multimodal analysis, scalability issues are there, fake news are there. So there are n number of gaps are there that we need to uh, address. And in conclusion, what I need to say is, of course, this all about technologies I already spoke. So here, if you take about Sustainable Development Goals (SDGs), so there is a huge alignment of Twitter sentiment analysis with the SDGs. We have SDG 3 alignment in analyzing public sentiment on diseases, vaccination, mental health, and healthcare services, quality education. We can collect the feedbacks from online learning experience and educational policies. So, like this, we have so many SDGs that are aligned with our Twitter sentiment analysis as well. So, in future, we can develop multimodal sentiment analysis models by integrating text, images, videos, and audio for richer opinion mining. And of course, it is a challenging work. So still, it requires implementation in future and enhance the detection of sarcasm, fake news, and contextual sentiment. Still, it is under discussion. Yes, this is actually my presentation. Thank you. Any questions, please?
Thank you, Abhilash. There's no questions in chat, and so we'll move on to the next presentation.
Thank you. Thank you, madam.
Our last presentation for today is by Ria Javali, who will be presenting use of dual verification and authentication and key agreement for enhanced security in 5G networks. You may now begin your presentation.
Yeah, I'm just sharing my screen presentation.
All right.
Yeah, so is this visible?
Yes, it is.
Yeah, so good morning, everyone. I'm Ria Javli from Kelly Technological University, and today I'll be presenting our paper titled Use of Dual Verification in Authentication and Key Agreement for Enhanced Security in 5G Networks. This work proposes a dual verification mechanism to strengthen the existing 5G AKA protocol and validate its security using cipher formal verification tool. So these are the contents that I'll be talking about today. So authentication is the process of verifying the identity of users and devices before allowing them to access the network. In 5G, it plays a critical role in ensuring secure communication and protecting the user privacy, preventing unauthorized access, and like maintaining the overall network integrity. The authentication in previous generations, authentication has evolved significantly across different generations. While 2G relied on one-way authentication and 3G introduced mutual authentication, 4G has improved key management through EPS AKA, but still it remained vulnerable to attacks such as IMSI catching. 5G overcomes many of these limitations by introducing SUCI to conceal a subscriber identity, stronger key management, and the flexible 5G AK authentication protocol. There are security challenges as well, despite these improvements in areas such as resource management, mobility management, etc. These challenges motivated us to explore the stronger authentication mechanisms. So these are some of the papers that we surveyed into, and so the summary is that the existing approaches mainly focused on blockchain-based identity management, AI-assisted authentication, and stronger cryptographic techniques. Most formal verification studies validate existing protocols using tools like ProVerif or Cyther. However, there is still scope to strengthen the authentication process itself, which motivated our proposal, which is the dual verification model. So the existing 5G AKA protocol, the user equipment sends its identity to the serving network, which communicates with the AUSF and UDM to obtain authentication vectors such as RAND, AUTN, and XRES. After successful challenge response verification, session keys are established. Although this protocol is secure, the final authentication mainly depends on the home network. In the proposed model, this is a main contribution of our work. Instead of relying uh, on the AUSF, our model introduces dual verification, where authentication is performed by both serving network and the authentication server function. The SEAF performs an initial verification using the received authentication response, while the AUSF performs the final verification before confirming the authentication. This approach improves security because authentication no longer depends on one single entity. This is particularly useful during roaming, where the serving network can perform local verification before the home network completes the authentication process. Overall, the model will strengthen the mutual authentication while also remaining compatible with the existing 5G architecture. So this block diagram summarizes the communication among UE, SEAF, AUSF, and the UDM. The key difference from the standard protocol is the additional verification performed at the SEAF before authentication is finalized at the AUSF. We have performed validated all our response in the Cyther verification tool. The Cyther model models the communication between protocol participants and automatically checks for the authentication secrecy and attacks such as replay attacks and man-in-the-middle attacks. And the authentication process begins with the UE sending concealed identity, which is the SUCI, to the SEF. The SEF will forward the request to the AUSF, which will retrieve the authentication vectors from the UDM. The UE responds to the authentication challenge, after which SEF performs the first verification, followed by the USF performing the final verification. Once both these verifications are successful, secure session keys are established. This is Cyther results. As you can see, all the key vectors such as CK, IK, the status is okay. That means there are no attacks. This table compares our work with the previously published authentication protocols. Earlier studies verified a limited set of security parameters. In our work, Cypher successfully verified additional parameters, including SUCI and the session keys, providing broader security verification while satisfying the required authentication and secrecy properties. To make the protocol, to validate the protocol, we have also done a Python check for this. This slide shows the protocol implementation in the Python. You can see that it produced successful verification results as presented earlier. The discussion, the proposed model strengthens authentication through flexible key derivation, improved mark generation, secure message integrity verification, and protected key exchange between the network entities. Together, these improvements will enhance the overall security of the 5G authentication process. Future work can focus on stronger privacy-preserving authentication techniques, improve protection through sequence numbers, and the integration of post-quantum cryptographic algorithms for the next generation networks. To conclude this work, it proposes a dual verification approach that strengthens the existing 5G AKA protocol with requiring major architectural changes. Formal verification has been done using Cypher, which confirms that the proposed protocol satisfies the required authentication and secrecy properties while providing improved security coverage. Thank you. I would be happy to answer any questions.
Thank you, Ria. There's no questions in the chat. You may stop presenting. We'll move towards the closing remarks now.
Yeah, thank you.
All right. So I would sincerely like to thank all of our authors for their excellent presentations and contributions in this session, and all our participants for being a part of this international conference. I hope the session was informative, and on behalf of the entire team, I would like to thank you for your support during this 11th version and all the previous 10 versions of the conference. We will be happy to have you in the 12th version in 2027. All the presenters will be getting their digital certificates via email in the next 2 working days, and the publication will be live in 7 to 8 months. Kindly cooperate with the team of ICT4SD 2026. I would also like to thank our session chair, Dr. Kalyan Devappa, for chairing this session. And on behalf of the entire team, ICT4SD 2026 and Global Knowledge Research Foundation, this is a token of our appreciation. Thank you so much for your valuable presence, and I kindly request everyone to please turn on their cameras for a quick virtual snapshot. All right. Thank you so much, everyone. The session is adjourned.